Understanding string theory, the fabric of the universe. String theory is one of the most fascinating and complex ideas in modern physics. It suggests that the fundamental particles we observe, like electrons and quarks, are not points, but tiny vibrating strings. These strings are so small they're far beyond our current ability to observe directly. But despite their size, they could hold the key to unlocking the deepest mysteries of the universe. What does this mean for the nature of reality? String theory proposes that the universe consists of multiple dimensions beyond the three we can see. But how do these strings work? And why do physicists believe they could unite all the forces of nature into one theory? In this video, we'll dive into the basics of string theory, explore its implications, and examine the challenges scientists face in proving its validity. Let's start with a basic question. Why are strings so important? String theory didn't just appear overnight. It began in the late 1960s when physicists were trying to understand the forces that govern the universe, specifically the strong force, which holds atomic nuclei together. Researchers noticed that a mathematical model involving vibrating strings could describe the behavior of certain particles. These particles didn't behave like point-like objects as previously thought. They acted more like tiny vibrating strings. The breakthrough came when physicists realized that string theory could potentially solve long-standing problems in physics, including quantum gravity. Quantum gravity is the attempt to reconcile the principles of quantum mechanics, which governs the behavior of tiny particles, with general relativity, Einstein's theory of gravity. General relativity describes the universe on a large scale, while quantum mechanics rules the microscopic world. The issue has always been that the two theories are incompatible. String theory, however, holds the promise of unifying these theories into a single framework, known as the theory of everything. But to understand how this works, we need to look at the basic components of string theory and how they differ from traditional physics. In the early days of string theory, it was originally conceived as a potential theory to explain strong nuclear interactions. However, as the theory evolved, scientists discovered that the underlying mathematics of string theory also offered an elegant solution to some of the most perplexing problems in physics, particularly those related to quantum gravity. Quantum mechanics and general relativity have long been two separate pillars of modern physics, yet they operate in very different realms. Quantum mechanics governs the subatomic world of particles, while general relativity explains the gravitational behavior of large objects like stars and planets. The incompatibility between the two led to what is known as the quantum gravity problem, how to explain the force of gravity at the quantum level, where the rules of classical gravity as explained by Einstein's general relativity simply don't apply. String theory emerged as a potential solution by suggesting that gravity could be understood through the vibration of strings that exist in multiple dimensions. String theory suggested that rather than point-like particles, the fundamental building blocks of the universe are vibrating strings of energy. The unique vibrations of these strings correspond to different particles, such as electrons, quarks, and neutrinos. This insight gave rise to the idea that on a fundamental level, the universe's matter and forces might all be linked through a single, unified theory, a concept that would eventually come to be known as the theory of everything. This theory implies that all forces in nature, including gravity, electromagnetism, the strong force, and the weak force, could be united under the same framework, creating a single, comprehensive understanding of the universe. The quest for such a theory of everything has been one of the central challenges of theoretical physics, and string theory remains one of the leading candidates to achieve this monumental breakthrough. One of the most surprising aspects of string theory is that there isn't just one version of it. In fact, there are 5 main versions of string theory, each of which describes the universe in slightly different ways. These 5 versions were developed over time by various physicists, and each was based on different mathematical structures. The 5 versions are Type 1 string theory. This theory involves open and closed strings and is related to gravity. Type Ia and Type Ia string theory. These are two different forms of the same general theory, with Type Da3b containing special features like supersymmetry. Heterotic SO 32 string theory focuses on the behavior of strings in higher dimensional space. Heterotic E8xe8 string theory, a version that's particularly relevant to some ideas in particle physics. These 5 versions were initially thought to be completely separate theories, but in the 1990s, string duality was discovered. This means that they are actually different ways of describing the same underlying theory, just like how different languages can describe the same thing. This unification is a breakthrough that has helped propel string theory forward. String theory doesn't just challenge our understanding of particles and forces, it also opens up the possibility of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. According to string theory, the universe may actually have 10 or 11 dimensions, with the extra dimensions tightly compactified, meaning they are so small that they can't be observed in everyday life. These extra dimensions are fundamental to string theory because they allow strings to vibrate in different ways, and each of these vibrations corresponds to different particles and forces. This leads to one of the most mind-bending implications of string theory, the concept of the multiverse. If there are extra dimensions beyond the ones we can perceive, it's possible that there are many other universes, each with its own set of physical laws and constants. In some of these universes, the forces and particles that we know could behave completely differently, or the conditions could be completely incompatible with life as we understand it. The multiverse theory suggests that our universe, with its specific laws of physics, might be just one of an infinite number of parallel universes, each with its own unique properties. However, the idea of the multiverse is highly controversial. Some physicists argue that it is speculative and beyond the realm of testable science, while others believe it offers an elegant solution to some of the unexplained phenomena of our universe, like the fine-tuning of constants that make life possible. While string theory has provided some insights into the potential for a multiverse, there is still much to learn about how to test these ideas and what implications they might have for the future of physics. One of the most fascinating and speculative ideas arising from string theory is the existence of extra dimensions. While we live in a universe that we experience in 3 spatial dimensions, height, width, and depth, and 1 time dimension, string theory suggests that additional dimensions could exist, but they are curled up or compactified to such a small scale that we can't detect them with our current instruments. These dimensions could be as small as the Planck length, which is about 10 to the minus 35 meters, much smaller than the size of subatomic particles. These extra dimensions aren't just a theoretical curiosity, they are crucial for the consistency of string theory. In the mathematical framework of string theory, the vibrations of the fundamental strings correspond to particles, and in order for these strings to vibrate in a manner that produces the forces and particles we observe, the theory requires the presence of more dimensions than the familiar 4, but this is where things get even more mind-bending. The presence of multiple dimensions opens up the possibility that our universe is just one of many, potentially existing in a multiverse. This concept suggests that there could be a vast array of different universes, each with its own set of physical laws, constants, and even dimensions. Some of these universes could be very similar to our own, while others might be radically different. The idea of the multiverse could explain why certain constants in our universe appear so finely tuned for life. Perhaps in other universes the constants are set differently, and life is impossible. The multiverse theory raises philosophical and scientific challenges, particularly when it comes to testing its validity. While it offers intriguing possibilities, it also ventures into the realm of speculative science. Some physicists argue that the multiverse is not directly observable, which makes it difficult to test or falsify. Yet others suggest that advances in theoretical and experimental physics could one day shed light on whether or not our universe is part of a vast multiverse. String theory may still be in its infancy, but its potential to revolutionize our understanding of the universe is immense. By offering a framework to unify the forces of nature, string theory could change everything we know about space, time, and the very fabric of reality. As scientists continue to explore its implications and search for experimental evidence, string theory stands at the forefront of theoretical physics, challenging our concepts of the cosmos. While we don't have all the answers yet, string theory opens the door to possibilities beyond imagination. The journey to understanding the universe is just beginning, and who knows what discoveries lie ahead. Thanks for watching.